for the next few hours, we'll talk about I/O performance, I/O sleuthing, and we'll try to figure out a little bit more how we can understand what's going on these complicated systems that are being deployed now and in the future. My name is Rob Latham, and I'll be your host for the next few hours. I'm trying something a little different in this talk. I'd like everyone to refer to the GitHub page where I've got a collection of examples and some scripts. And I'm going to try to use the GitHub discussions feature so that we can continue talking about this after the talk. And people who come across this video in the future can see the conversation as it happened or be part of the conversation throughout time. I don't know if it's going to work out well or not. This is a new thing for me. I'm looking forward to seeing what happens there. I'll tell you a little bit about myself before we get too far on. I don't have a PhD, which makes me somewhat unique at Argonne. Lots of doctors around here, but me, I got my start after getting my master's degree from Lehigh University. I got a lot of experience using Linux in the college dorms, trying things out with some friends. And then amazingly, first job out of college, a chance to play around with Linux at a much larger scale. There's a small company local to Lehigh University that was selling Linux clusters. Back then we called them Beowulf clusters. But there were Linux clusters that applications folks in pharmacy and in computational fluid dynamics and in other domains, cancer studies, would buy these machines. They were pretty good for price performance. Sometimes they couldn't do everything that at the time the large vector Cray machines could do, but they were a pretty low cost and used commodity components to achieve a higher science throughput than you could with your, say, one desktop. And it was not a bad price. So on these systems, we use a lot of Argonne software. We used MPI, we used MPIG from Argonne. We used a parallel file system that was being developed at Argonne. And so when Rob Ross at Argonne said, hey, why don't you try out this job we got over here? I was happy to come out to Argonne, and I've been here for about 20 years. It's been great. And one of the themes throughout both my first job and at Argonne is how, yes, the software and the technology is a lot of fun, but the emphasis has always been on helping applications use this software and use this technology to do something, right? They're trying to not create some stunt benchmark, but trying to model a protein folding or design a new piece of material. And often I/O is the challenge in that. So in 2022, I was selected as a BSSW fellow, and so I'm presenting this work as a chance to help the community be as excited about I/O and using I/O, fixing I/O problems to help applications in the way that I've been doing for all my career. This is an I/O talk. We've got a lot of themes about I/O in this talk. First off, it helps to sort of step back and think, do you have an I/O problem? And I often ask an audience this question, and most people will not raise their hands. And I feel like sometimes that is that these people don't know they have an I/O problem yet. Often scientists are so busy getting the science correct, the I/O becomes an afterthought. And then once we start scaling up and running in larger systems, all of a sudden we need to start digging into I/O and figuring out what's going on. So where is the I/O problem? We've got a bunch of tools and resources to help dig into that very problem and try to figure out why is this I/O pattern correct? Is the performance what we expect? Which layer of the software stack should we look at to understand better how to get that performance? And then, of course, what are the tools? What do we have to fix it? And often those are some low-level tuning parameters, maybe a different choice of I/O libraries or some other approaches. And if you want to learn even more after hearing me talk for several hours, that would be great. We've got a whole bunch of resources linked in this presentation. but also we can have a conversation through the GitHub activity, the GitHub discussions, and we can talk through email or other sources too. There are a lot of fun quotes about storage. I don't know when he said it, or even if this is actually a Ken Boettcher quote, but I love this quote, that a supercomputer is a device for turning compute-bound problems into IO-bound problems. So back when we had stupid computers, little tiny desktops that couldn't do anything, IO was not the most important challenge. Instead, it was, how do we keep the CPU cycling as fast as possible? How do we optimize the code to run? And then if the IO took a little while, well, that's okay, because it took 3 days to do a frame of a ray tracing graph or whatever your application was. But now the balance between compute and IO, not now, the balance between compute and IO keeps shifting in such a way that you can do more and more compute in less and less time. And IO, while it is improving, is not improving at the same rate. Our astrophysicist friends have been a big help in the community. One of them told us at a SciDAC conference, there is no physics without IO. So it's enough you can model the stars and the galaxies, but until you've fed those simulations with a fairly large input deck, or save the results to a compelling video or a visualization or another other analysis of what's going on, how can you really tell what is happening in your computational simulation, and how well does it match with reality? And in that same vein, very few large-scale applications of practical importance are not data intensive, right? If your computation does not need a lot of input to get going and isn't producing a large amount of output, there are not many domains where that is going to happen. We know a few domains where after computing a while, the answer is a small integer. Okay, but that is in the minority. Mostly we're trying to depict a very detailed model of some real world phenomenon. All right, so as we talk today, I'll talk about some of the challenges we face in IO. What are we trying to accomplish in IO? Right? The job is not just benchmark this file system or this hard drive, but the job's usually more as one part of a larger ecosystem, an application, a workflow, and where we fit in the broader context. I'll talk a little bit about file systems, because even though as users of these systems, you don't really get much choice in which file system has been installed on these machines, we do get, it helps understand the technologies and what's going on, and it helps understand why certain patterns might perform poorly, or how can we get file systems at this scale to behave. We'll talk a bit about benchmarking, because there's a little bit of a trick to it. Benchmarks are often synthetic codes, so they don't exactly behave like applications. As a result, they may not, out of the box, show you the kind of results you expect. So we have to talk a little bit about some benchmarks and how we can get them to behave the way that an application behaves, and how we can interpret those results. We'll talk a little bit about a specific file system, the Lustre file system on the Polaris machine at ALCF. As a part of collecting these materials, I logged onto Polaris and started doing the same kind of things that I would do on any system to understand what's going on and how the various tuning parameters we have reflect in IO performance. Then adjacent to benchmarking are the tools we have to understand what's happening inside these IO libraries. And I'll spend a lot of time talking about a tool called Darshan. It's an analysis tool we developed at Argonne, and it has, in some ways, very much simplified our job as IO researchers, but also opened up many more questions about how we can even better meet the needs of application scientists. I'll take a little bit of a break halfway through. we'll catch our breath, get some water, and then we'll go to a little bit higher level of the software stack. We'll talk about the MPIO library, which is something I spent a lot of time working on. We'll talk about some of the higher level IO libraries that sit on top of MPIO, like parallel.cf, HDF5. And at the end towards the end of the talk, I have an example of a machine learning oriented benchmark. My background is in storage, file systems, libraries, and so I am not very well fluid or fluent in the machine learning frameworks that everyone's using for such great impact these days. I'm also not a computational physicist or a material designer or an astrophysicist, but that has not stopped me from helping these domain scientists improve their throughput and improve their scientific productivity. And so we'll talk a little bit about how that works in a somewhat newer domain, machine learning. Okay. I marinate in this topic. I live in this world for decades. And so I'll often use terms and technologies and terminology and phrases that may not apply or be familiar to the broader audience. So let's take a little bit of time to talk a bit about the bigger picture and where my work and where this presentation fits in. So computational science is right there in the name. It's the art of using computer simulation to help us better understand the real world. We can't always experiment on the large scale problems on a laboratory workbench, or if we can, it's at a relatively small scale, and then the computer model can help flesh out a more deeper understanding of what's happening. Now, as these physical and chemical and material problems get larger and more complicated, we need more and more sophisticated machines to capture that level of resolution and detail. And that means larger machine, more components, more pieces. That means splitting up our tasks to be parallel across CPUs. It means being mindful of network interlinked imbalances. It means being mindful of storage. Because in order to drive these computational simulations, we need to think about how to work with the large storage systems that are paired with these high-performance computing systems. Now, it's not quite the same as using your laptop or your cell phone or other individual devices, because in this case, we've got parallelism across the storage devices as well. And these parallel storage devices are shared among the whole compute system and all the users of that compute system. So we've got quite a few challenges here. So being able to extract parallelism, but also understand what's happening so we can get even more parallelism are important aspects. And one of the reasons why it is a little bit challenging is because application scientists think about their data, well, the way that the application scientist data exists in the real world. We don't think about a collection of bytes on a disk. We think about a tree-based hierarchy of containers. Maybe there's a data structure, like an adaptive mesh data structure that is helping to gradually and increasingly refine the mesh over a multi-scale algorithm. For example, in this figure here, we've got an element of a nuclear reactor. And on these nuclear reactors, we have fairly large scales. The fluid flow as the coolant loop maintains it extracts heat from this fuel rod, but also there's neutrino level interactions as we try to understand the role of the inhibitors and the fuel rods and how that all fits together. So there's a lot of complexity here. And the data model that the application is using to track all of this data may or may not be a good fit for what's going on in storage. Well, as a result, we have to think a little bit more about how we're going to save that data, how we're going to use that data, and how that data is going to be used not just by this application, but by other people in the ecosystem. As with all things in computer science, we can fix this problem with more and more abstraction layers. And we've pretty much settled on these 5 or 6 layers of the software stack. Working from the bottom up, each layer adds a little more context, a little more structure to the data. At the very bottom, we just have the raw I/O hardware, storage, the disks that are holding the data, or tape or SSDs, whatever it actually is, deployed to these systems. I think we're talking about thousands, tens of thousands of actual little storage spinning devices looped together in some kind of parallel file system. Because we're not going to write individual disks, we're going to let the parallel file system aggregate all those storage devices into one presentation, presented as one unified container of data. This red layer here, the I/O forwarding layer, it comes and goes through the history of these machines. There was a time when there was a pretty actively investigated layer because the scaling of the machines had outstripped what the file systems could deliver, and so an I/O forwarding layer helps make these file systems help manage the clients. And so these file systems only saw a smaller number of clients as they were trying to deliver parallel performance. And then the latest machines, I don't think there's too much I/O forwarding happening right now. Working up again, I/O middleware. Now you have a parallel file system. You have, on one hand, you have lots of clients. On the other hand, so this middleware layer starts talking about programming models. In this case, I'm going to talk about the MPI/IO programming model, but and the I/O middleware there is the MPI/IO library. But you can imagine a middleware showing up for other domains as well, being a better fit for workflow-oriented computational tasks or other domains like that. Once we have these building blocks in the I/O middleware layer, a higher level library that starts talking to the application in terms of what the application is expecting, it sort of kind of seals the deal there. And we'll talk more about what that means in the second half of today's talk. I speak broadly about storage, about data, but there are several different ways, quite a few different ways to store that data. Commonly, file systems, both the ones that are on your laptop, but the parallel file systems that are on these machines have very distinct characteristics, a directory of files and operations on those files. But over the last decade or so, that's getting a little more, this ecosystem is getting a little more robust. So a few more options. Blob storage has this notion of we'll just put a big chunk of data into this storage repository, maybe it's Amazon S3 or some other option, and then we'll get that back when we need to. And the application knows how to deal with the blob and everything else is going on. I just need a place to put a bunch of data. Maybe you have a little more structure of that data. Classically, databases have been great for learning more about what kind of data you have and what's going on. And we do see scientific databases. The workflow is a little challenging to do it at parallel scale. So I'm not going to talk too much about that, but that's another option. And key value storage for lots of small data. We see log structured merge trees and other technologies coming out of the hyperscalers, the Facebooks and the Googles. Again, won't talk too much about that, but that's another approach to dealing with storage if your data naturally fits into a bunch of keys with a relatively small amount of data associated with each key. Because we only have 3 hours, I'm going to focus on the Lustre file system. A lot of these file system discussions about parallelism across servers and lock management will apply to other things like GPFS or other file systems you might have exposure to. But we're going to spend a little bit of time talking specifically about the Lustre file system. Now, then the software abstractions that are on top of there help us achieve something that we shoot for called performance portability, where you can provide all this information to your application and hopefully achieve good performance when you take that application to a different platform, that all the tuning and low-level details that you did for one machine, either they'll be applicable to different machines, or you can have a different set, hopefully a small set of site-specific tuning parameters as you go from machine to machine. It would be great to have almost no site-specific tuning parameters, but we're not quite there today. All right, so parallel file systems. Let's get right into this. Conceptually, we have a little cartoon about a parallel file system, and we've scaled things down to human scale. The amount of parallelism in a modern day parallel file system would be much larger, but you may have a collection of big, fairly large files or fairly small files. The parallelism from a parallel file system comes from striping these files across more than one server. So in this case, simple example, 4 servers. This data, this large checkpoint file has been sharded across these 4 servers. And there's a little bit of metadata assigned to each file so that we can talk about the name of the file and some permissions. When the application at the high level talks about an offset into a file, that application is actually going to be translated into a specific server, a specific disk on that server, and then a specific location of the chunk of data on that server. So we have a lot of indirection here, which is part of why it's difficult to get the best performance right away. Yeah, another complication is the locking that goes on in parallel file systems. Each file system has a different way of handling this, and when I talk about locking, there's 2 kinds of locking. There's the explicit user-induced locking. The user says, I don't want anybody to access this data. Give me exclusive access to this region, and I'll work to it for a little bit and then let go of that lock. When I talk about locking in a parallel file system, I'm often talking about the implicit locking that's in the file system, so that when multiple clients write to the same region of the file, there is some serialization that happens there and prevents a corruption of the data. Now, the reasons why we have to worry about this so much are kind of tied up in the legacy interfaces to these file systems. But the end result is you can picture a file, and let me switch to a pen here. No, laser pointer, please. Okay. You can picture a file, and it's split among the different units of the file, and each unit of the file, maybe it's a page of memory or a block on the file system. So this could be anywhere from 4 kilobytes to several megabytes. But it would be too difficult to have exceedingly fine-grained byte by byte locking. Instead, each region of the file, and region is one of these boundaries, controls one set, some number of bytes of data. But this file access in green here is now striding across, say, it touches 3 different lock units. And so the file system will, under the hood, serialize and exclusively access those 3 regions. Now, even if you wanted to write, another process came by, wanted to write over here to the side of this region, that would not be able to happen. The lock boundary is set across each of those pages. All right. No, again, I want to spend a little bit of time talking about a specific kind of file system, the Lustre file system. And there's a little bit, I will try not to use the terminology of Lustre. There are the clients, and there can be quite a few Lustre clients. The terminology is that they have a metadata server, or MDT, and each of these object storage targets, the actual device that's holding data, sometimes called OST, is published or sent out to the file system through these object storage servers or OSSs, I'll try to use terms like servers and devices and not get too caught up in the specific terminology of Lustre. And then there's a network of some kind, usually shared with the compute side of things too. It helps all these clients and talk to the servers as fast as possible. The client interface to Lustre is a POSIX interface, which is the one you might be familiar with from from any kind of programming you may have done in a Unix environment. We open a file, we write some data, we read it back, and we close the file. This old interface dates from the 70s, doesn't have a lot of information about parallel accesses or multiple clients doing the same thing, because when it was designed, it was the case that you only had your system you worried about. You didn't often worry about accesses from somebody else. It's just one application going through the operating system. Or if there are multiple applications, then the applications would sort that out. But okay, so here's the topology of Lustre. Now, hold on to this thought for a little bit. I'm going to take a little bit of a detour as, well, not exactly a detour, but I want to talk a little bit about benchmarking these parallel file systems. And now we know what a parallel file system looks like. We can talk a bit about how we're going to exercise those file systems. Now, first, I want to thank Glenn Lockwood, a longtime friend of MCS, a friend of Argonne, who is now working at Microsoft, but is still the maintainer of IOR and this benchmark. Benchmarking in a parallel fashion is, in some ways, it's easy. You allocate some data, you write out to the file, you measure the times, and then you report it. But there are enough subtleties that it helps to have sort of a community established benchmark. If I run some IOR numbers and I tell somebody, hey, I ran IOR, the interleaved or random benchmark, but the name is kind of an old name now. It's called IOR for historical purposes. It's just IOR these days. If I run this benchmark and I give my results to somebody, they'll know what I did and how I configured it, and we'll be speaking the same language when we talk about the results we get. The other advantage of IOR is it's MPI oriented, and again, we talked a little bit about programming models and middleware layers. Almost all of the applications running on machines at ALCF are MPI based, or either task based with an MPI dispatcher. But the fact that we have a benchmark that can use MPI to spawn all these processes, measure the performance, and report back, means that IOR is going to be useful as from very early stages in the deployment of a cluster, of a compute system. There's a couple, I'll get tripped up on this too. There's the block size and the transfer size parameters. The way to think about that is, I'll switch back to my pen here. Transfer size is each client is going to send data in units of transfer size, and then the block is how big a region of the file has been allocated to each process. So here, rank 0 is going to do, say, 4 writes of some transfer size out to this file and then read back 4 size. And then segment is how often is this pattern repeated? So in this case, we have 3 ranks here, and they're going to work on this part of the file and go over this part of the file. And you would maybe do segments if you wanted to make sure you're testing. You just want to repeat pattern a few more times and get more data through to the file system. The great thing, so I said, IOR is very contiguous, very structured, very oriented towards contiguous transfers of data. There are some ways, as we'll see later, to do non-contiguous I/O, but with this contiguous exercising of the file systems, we can also slip in other interfaces. We could just use POSIX I/O like we showed before. We could switch to MPI I/O. We could use high-level libraries like HDF5 and Parallel CDF. Now, using those high-level libraries is kind of weird because those libraries are set up to do non-contiguous, they're generally set up to do structured data out of an array or some kind. We'll talk about the differences there. So it can be a little bit weird to use HDF5 or Parallel CDF with IOR, but again, here's a case where we can have a simple workload that everybody using these libraries and tools can understand. Then we have newer interfaces like the S3 object store or Rados object store. And I think there's a few more options in IOR these days. Check it out on GitHub and give it a shot to get sort of a sounding point of storage performance wherever you are. But there are a couple pitfalls. I did mention that it's a little bit tricky to do benchmarking correctly. So in this case, we have a file system that was spec'd at 120 gigabytes a second. You'll deploy a file system, the vendor will say I can do 120 gigabytes a second. So you have a small test here, 4 compute nodes, 16 processes per node, so 64 processes altogether. A 1 megabyte transfer and a 64 megabyte block size, and we'll do 64 of these segments. And then, what happens here? Well, the write and the read size here are much larger than advertised, right? Instead of 120 gigabytes. Sorry, the write size is okay. The write size is much smaller than advertised. The read size is 4 times larger than advertised. So that's a little bit weird. What's happening here? Well, we'll talk a little bit about what's happening. If we can, let's back up a little bit. Talk about it. So what's happening? When we read back the data, okay, right. So we'll talk about why the write data is poor. We'll go right first. Because these processes all write into a shared file, I hate to say it, but splitting up into one file per process is a way to get some better performance. Except now we're talking about dealing with lots and lots of files. And the metadata server, the metadata component of the file system, needs to be involved in every one of the file creation and operations that happen to do all these files. So this can be a short-term band-aid, but it's not going to be, it might be the best solution long-term because you don't want to deal with tons of files as you scale up the problem. This is probably okay for 64 processes, but you have thousands and thousands of clients, maybe not so great. Again, the read side is still pretty high. So let's talk about that. Why is that so high? The Linux kernel, the OS kernel that's on these systems, has a page cache. And if we have a small amount of data, here we'll use this pen again. We see a region here. Data's real nice, fitting in cache. We can get tons and tons of performance. Now this is now measuring memory bandwidth, not really measuring file system bandwidth. And as we get larger amounts of data here, we're getting to a more realistic or a number that's more like what the OS, the file system has been spec'd out to deliver. Now, if you get really big, then we're hitting swap, and it can be pretty slow. So these caches are in. There are a lot of caches in the software stack, and so we can play around with a lot of these different parameters here. The number of 30 megabytes and how many pages per RPC that Lustre has. Maybe NFS has some things. I wouldn't recommend using NFS for your parallel file system. But the point here is, if you haven't disabled the page cache and then you do some benchmarking and then you read it back, you're going to be hitting the page cache and not the actual storage device. So one thing we can do is we can shuffle the clients around so that when we write the data from rank 1, a different rank will come back and read it. So in this case, we're getting a decent amount of data here. We're closing in on a more realistic number. But even more realistic is remember, writing is 2 steps here. We send the data off to the file system, but again, all these caches are involved. We can ask the file system, please sync that data out to storage. And when we think about how fast can I write to storage, really think about how fast can I put data on the disk. So when we talk about our benchmarking and our results, we're often talking about not just the write time, but the write plus sync time. So that's another thing to watch out for on the benching. Sometimes if you don't flush out the data, your close, maybe all the work happens in close, and now all of a sudden your close takes tens of seconds, and then you got to wonder, was close expensive, or was close dumping a lot of data during that operation? No, so here's that discussion pictured graphically, as we if we time the end of a write, are we timing everything, or sorry, top picture, we write the data in parallel, and we have an MPI barrier, and we say, okay, that took this long. But then all of a sudden, this close data happens at the end. This closing time happens at the end. Maybe a more accurate way would be to throw some F-syncs in there, and then you're measuring both the time to write and the time to push out the data. Now, this all depends on sort of what you're trying to do as an application. All right, so graphically picturing that, we have a few configurations here, and we can get some really highly variable numbers reading data out of this file system. It helps to understand why we might see what we call faster than speed of light numbers here on the naive and file process case, and then what happens as you are more mindful of the different caches that are happening in the file system. So here's a more example here about how you might run. The vendor delivers a file system, and you as the customer want to make sure it's showing the numbers that the vendor said. So you may run a large number of nodes and clients, and then do this with the -F flag. You're going to go file per process, and you're going to shift the ranks, and you're going to measure the time. And now we'll do. We're just going to write the file, and then we'll see what the results are. Now, is that accurate to your application? Well, it's probably not what every application is doing, but you have this trade-off of what I'll call wide benchmark versus a more application typical number. If you have a very large block size and large number of segments, you're going to show what the actual file system is doing, and you'll bypass the cache effects. But is that going to be like the user is going to try to do? Well, yeah, sort of opens your workloads and try to understand. All right. Give me a second here. I would like to talk about an actual system. This is the Polaris machine over at the Argonne Leadership Facility, just across the parking lot over there in the machine room in 240. But it's a pretty sizable machine. It's our exascale stepping stone machine. We're going to run here and learn some things about these larger scales and GPU accelerated codes, and then we'll apply that to the next machine that shows up here. But in terms of number of nodes, amount of memory, that's all interesting. But to me, the most interesting part is the Lustre file systems here. We have 4 different Lustre file systems. I'm going to be talking about the grand file system, which has a advertised speed of 650 gigabytes per second. We won't see that in our tests today. I'll tell you about why in the next slide. And there's a couple other file systems that have been around for a while. The Theta F0 is an old file system from the Theta machine, configured a little bit differently. And there's even older file system, a GPFS file system that dates back from our Blue Gene days. So that's even older. We won't talk too much about network effects in here, but we have a Slingshot 10 network, and there'll be an upgrade process to set it to Slingshot 11, which may impact some of these numbers, but I think for the most part, we're not hitting network limits in these benchmarks. So why is it so hard to benchmark these systems? Well, this is a cartoon. I'm not really actually measuring anything quantitatively, but when these machines show up, there are no users. Right? They're built, and the integrator is testing it out, and so there is a measure. They get the chance. They're the people. They have the one user using this machine, so there's very little contention to these file systems. There's some acceptance testing where a few of the say Argonne integrators are going to try things out that are to try to do the things that users want to do and make sure it's going to work as advertised. And now we're getting a few more users on the system. But then the early access comes in, and a few friendly scientists who know the machine might catch fire or fail in some way will try things out. And then it's in production. And what would be great is if I could get access to the machine as it's installed and have dedicated access to the storage for a week or 2 weeks or however long it takes me to run some benchmarks and really learn this file system really well. That never happens, right? The storage system is a piece of the machine, and we need to get everything running and the users using it as soon as possible, because these machines are not for storage stunts and storage benchmarking. These machines are to do science. So the goal is to get to the production side as fast as possible. Unfortunately, once we're in production, everybody's doing science on these machines. And so everybody is writing to these file systems and reading back to these file systems and creating files in these file systems. And that happens until retirement, and the machine is no longer interesting. And 5 years later, go ahead, use this machine all you want. We don't want it anymore. Well, now it's not interesting to me either. I wanted it 5 years ago. So when we run benchmarks, we're happy to use these machines during their congested contention time. We just have to be aware of that contention. All right, when we allocate nodes, you saw the examples from a few slides back. You use a job manager, you get access to some nodes, and those nodes are your nodes to use. Nobody else is sharing those nodes, depending on the configuration of the system. But they don't have that same sort of resource allocation and dedication in the file system layer. And so we'll have to be mindful of what's going on as we benchmark things. With Lustre, there's lots of ways to tune the file system, but I would like to talk about one specific way of tuning the file system, and that is the stripe count. As we talked before, these machines are parallel, which means two things. Parallel means more than one client is going to access these file systems, but it also means there's more than one server providing data that these file systems host or taking reads from these clients. We don't need to worry about the details so much as users. We can open a file, start writing data, and the file system will do that just fine. But if we know a bit about how that data is stored, and in this case, this checkpoint file has some chunks that are scattered around the 4 servers of this parallel file system. If we know something about that data distribution and the way data is laid out, we can understand performance a little bit better. So we're going to use the IOR benchmark. I want to draw your attention to this URL down here. Again, I've got a GitHub page where I put lots of examples up here. We can look at the details about how I ran these benchmarks, and maybe we'll find some mistakes or improvements we can make down the road. But anyway, show my work here. So over on GitHub, you can see how I ran this IOR benchmark. I used MPI-IO hints. We'll talk about MPI-IO and that layer in a few more slides, but we use these hints to vary the striping size of this benchmark file. And on Polaris, the default stripe size is over here on the left-hand side. It's 1. And so almost always, and throughout the day, we'll see a couple more examples of this. Your first experience with Lustre will be terrible. You'll run the parallel file and you'll get very, very small performance, much less than you thought you could get. Now, if we change the striping parameter to use more Lustre servers, we get much better performance. You can see in this graph here, this is 128 clients writing to the file system. Blue is the writing number. Performance goes up here, and we keep using more and more servers, and we get better and better performance. We're not getting advertised performance yet. I'll talk a little bit about why that might be. And the reads performance is quite a bit better, minus this weird error bar condition here at the highest number of stripe size. So I would say that for most large IO runs, use all the servers. That's LFS set stripe -1 and the file, or use the MPI IO parameters, or you do whatever you can do to use all the files. I think a couple of reasons why we're not getting the full advertised bandwidth. It's not the whole machine. It's about a quarter of the machine, and there's other things going on in this file system. And also, this is a shared file, so there's a little bit of Lustre lock management going on. We'll talk a bit about how we can work around that. in the MPIO section. There is one fun feature in Lustre called the progressive file layout. I've been waiting for this for a long time. It's not on by default on Polaris' file system, but you can request it and play around with it. And what is this? What is it? I glossed over this part, but why would a file system default to 1 or 4 servers for parallelism? Well, if you look at the distribution of all the file sizes on a parallel file system, or really any file system, there are lots of very small files. And these very small files don't parallelize very well. You can distribute them on a file-wise basis, but in terms of each file's parallelism, it's very hard to get a lot of parallelism out of a 4 kilobyte file. So instead of having a system where you have to opt into the most amount of parallelism, progressive file layout lets you do something else. Lets you say, okay, for every file in this directory or this file system, if it's small, here's this first region. If it's small is configurable, just use 1 server. As it gets a little bit bigger, please use a few more. And if it gets very, very large, use all the servers you can find. And once you've set that up, then you get this nice situation where all the small files in your directory are talking on just 1 server at a time. They don't deal with the coordination problem of dealing with multiple servers, but anything large gets a little more parallelism and hence a little more performance. This may be hard to read if you're in the back of the room, but if you look at these materials on your laptop or there, I have the output of setting up and requesting progressive file layouts on the Polaris machine. Okay. So here's a small piece of file, just test file. You set up the 3 regions here. For the first 4 megabytes, it's 1 server. For the next 256 megabytes, it's 4 servers. And then for the rest of the file, this -1, use -1, which means all the servers. And did it work? Well, we can use this LFS get stripe tool to get some output here. Lots of detail, but the important part here is the extent number here. So the first 4 megabytes are going to be in a count of 1. And the next 256 megabytes is count of 4. And for the rest of the file, to end of file, -1, which means all the servers. Great. So I will look forward to benchmarking progressive file layout stuff more in the future. So if I was going to summarize Lustre performance in 1 slide, I would say the absolute first thing, and for many people, the only thing you need to do, please use more than 1 stripe. All this OSTs is usually what you want, and that just makes everything work so much better. As progressive file layout is rolled out to more file systems, more sites, it's on by default. For example, at OLCF's Ascent machines, they're going to be the newest machines at OLCF. I forget the exact name. The newest machines at OLCF are using progressive file layout by default. Again, this is a somewhat new feature. So as machines like Nurse Perlmutter tries this out, we find some bugs in the different software stacks, and so we're being a little conservative here. Opt into it, get it, and try it out. I didn't get a chance to test all these other features. Overstriping is asking for more stripes than there are servers. That's been, at least in Cray and Lustre developers say that's going to work out pretty well to get good performance. When I tried using it, I asked for 300 stripes and I got back 160 stripes. So something isn't quite configured that way yet on Polaris. We'll figure that out. And again, I've talked about this a few times, but my break glass in case of emergency trick to get good write performance might be to use more than 1 file. But again, managing that many files is going to be a huge headache. And maybe as the creator of these files, you don't care that's some poor grad student's problem. But if you look holistically, a small number of files is going to be a lot easier to manage. And I'm pretty sure we can get, with a few tuning values, we can get back to pretty good performance. So we'll keep working on it. and get there.